Hello, welcome to our webinar on new features in LORENTZ. My name is Dennis Peterson and I'll be conducting today's webinar. I'll be demonstrating some of the enhancements we've made in version 9.1 of LORENTZ, and then we'll have some time to deal with any questions that you might have. We're going to deal with four main topics today. We'll discuss the new parallel launching feature and enhancements we've made to the emitters. We'll demonstrate the new analysis along a defined beam axis, our new Quasi transient analysis mode, and some new geometry tools. With version 9.1, we've introduced parallel ray tracing, and this dramatically increases the speed if you're launching a large number of rays. Basically, it allows you to utilize all available cores or processors that you have on your computer. The bar chart you're showing is basically summarizing benchmark tests we've done, and it shows that as your number of cores increases, the simulation speed for the trajectory increases. You can set the number of cores that LORENTZ will use using the settings dialog box. So the number of threads that you assign will be used both in the field solution and then when you actually begin ray tracing. We've made several improvements to the emitters. So now the emitter dialog allows you to define a number of emitters, but only the selected emitters will be used for any particular beam. In addition to point and surface emitters, we now have segment emitters. We've improved the way emitters are displayed in the workspace, which is a great help when you're editing emitters. And we now have the ability to assign colors to emitters, and the trajectory dialog box will automatically automatically display the emitters' colors in the trajectories. So here I'm just showing a portion of the emitters dialog box in version 9.1 and version 9, and you can see that you can have several emitters defined in version 9.1, but only those that are checked will be used in a particular beam analysis, which is a great convenience. Segment emitters can be very handy if you're looking at, say, the launch of beams along focusing or defocusing axes. You're launching only a few rays, so the simulation will occur very quickly. Here I'm just showing an example where you have several emitters. We have some point emitters and some surface emitters. And as you're editing emitters, any emitter that you select will have its cones displaying the emission direction, and the selected emitter will have larger cones than the other emitters. And as I mentioned, we can now assign colors to emitters. That makes them easier to edit. And also, when you're looking at trajectory results, by setting the solver setup so that the color of the beam is according to the emitter, you can see which part of a beam came from which emitter. I'm going to demonstrate these features using a periodic model of a magnetic quadrupole. So here's our model. And it's a periodic model, so I've modeled only one pole of each quadrupole. And I'm showing here a contour plot of the X component of the magnetic field along the path of a beam. You'll notice that there's one beam displayed. The beam was launched directly down the optical axis. The areas in the contour plot that have a light green have essentially zero a magnetic field, which is what you want in a focusing mechanism. The red areas have a positive X component and the blue areas have a negative X component. Now I've launched other beams here. The second beam has been launched along the axis from points which will be initially focused by the first quadrupole, and there'll be a slight defocusing from the second quadrupole. And the last beam I launched also is from 2 points. These would be on the axis which is initially defocused by the first quadrupole, and it will be brought into focus by the second quadrupole. So now I'm just going to temporarily turn off these trajectories, and then we'll zoom in on this area, and we'll define some segment emitters just to show you how that's done. So here we have the new emitters dialog box, and you can see that I have 3 emitters already defined. The first emitter is a point emitter right at the center, launched down the optical axis. The second emitter consists of 2 points, and those are on the axis which is focused by the first quadrupole. And the last emitter that I've defined has 2 points, and those are on the axis which is defocused by the first quadrupole. So now I'm going to add some segment emitters. So we'll add a new emitter defined by selected segments. And we'll pick these 2 segments which are on the axis which is initially focused. Now you notice when you first selected them, you have a number of choices for the emission direction. What we're showing here is random launching perpendicular to the segment. That could be useful if you have a heated filament which is emitting electrons in all directions. In my case, I want to fix the direction. I want them to be launched right along the z-axis. I'll change that. So now I've defined the segment emitter and its direction, but I haven't defined the particle. If I launched it now, it would accept the electron particle with the 0 energy. I want to launch a cesium ion instead, and I want it to have an energy of 300,000 electron volts. Now I'll add a second segment emitter, and this time we'll pick 2 segments which are on the axis which is defocused by the first quadrupole. And once again, I want it launched in the z direction. Now you notice initially all these are colored blue. I'm going to change that color and make it red, just so that it stands out better, and also so that the beams later on will have a different color. Once again, I'll use cesium ion with 300,000 electron volts. Okay, so that defines our new emitters. Oh, hang on a second. Let me just check something here. Go to emitters. Oh, let's make sure we don't want to launch that other emission. So we're only going to launch these 2 segment emitters for the next beam. All right, and now we'll zoom back out. Now I'm going to change the trajectory solver setup. And we'll set the ODE to an adaptive RK5. And we'll set the appearance to a conical appearance with the same color as the emitter. And now we'll run the next beam. Okay, so now you can see we have 2 new beams which are launched from the segment emitters. And you can see there's a focusing action first for the rays from the blue emitter, and then initially there's a defocusing action for the rays that were launched from the red emitter, but after they pass through the second quadrupole, those become focused. Now, so far I've just defined segment emitters using straight line segments. You can also have segment emitters which are defined by arc segments. So in this case, I've created emitters along these 4 arcs, and again I've launched them in the z direction. And this gives you a very good visualization of the envelope of the beam. So here again, as you adjust your view, you can see the different focusing and defocusing effects. Now this is beginning to get a bit cluttered though, okay, and if you were to launch from a surface a large number of rays, as you would want to do if you want to look at statistical effects or space charge, then interpreting the results can become difficult. So for that reason, we've introduced a new optical axis or a beam axis which you can set and then perform plots and analyses along the axis. So here I'm showing the beam display along axis dialog box, which we use to make plots. And I'm showing a portion now of the beam axis definition dialog box. You can define a beam axis along any of the principal axes or any collection of connected segments. So let's do that now with, again, our quadrupole model. And in this example, I have a surface emitter, and I've launched 120 rays. So now you can see the display is getting a bit cluttered. In this case, I'm just using a line display instead of the cones, but still it becomes difficult to interpret what these results are. So we can define a beam axis. In this case, I've used the z-axis. And I've set the origin not at the emitter. I set it where the beams start entering the quadrupole. So now we can perform different analyses along the axis using the beam display along axis box. So let's first do a scatter plot of the number of rays right at the start of the beam axis. And you can see you have an essentially uniform distribution of rays because they're just starting to enter the quadrupole. We can go on a little further. Now you're in the middle or the center of the first quadrupole. And now you begin to see the compression effects. Now so far I've been entering distances along the axis. You can also just pick points along the axis. And in addition to showing the number of rays, you should show current density, charge density, the time, the energy, the momentum. I'm going to now create some contour plots of the current density, and I'm going to use solid colors. So once again, we'll do it right at the origin, and then right in the center of the first quadrupole, and between the two quadrupoles, and just at some arbitrary points. Now you notice as I continue to make these plots, the colors change because the current density is getting larger as the beam gets compressed. So here where the beam is compressed, you have a very high current density, and that changes the colors in the initial plots. Now maybe at this time it'd be a good idea to just launch one of our poles. So basically we have a question for the people who are attending today, how often you're performing trajectory analyses which requires a time varying solution. And it seems like about half of you so far, as I'm watching the polls update, are requiring time-varying fields. Okay, well that's very good, because that brings me to the next feature that we've introduced. We now have a new quasi-transient analysis feature. So if you're familiar with our programs, you know that you could always do static and phasor analysis and transient analysis for electric fields. Quasi-transient analysis is a simplification of the transient analysis, which can be performed much faster. Basically what happens in a quasi-transient analysis is that we rebuild the field using superposition and scaling. So it's not actually performing a true transient analysis, but the effect is that the particles being launched in a trajectory simulation will see the time-varying fields. To perform a quasi-transient analysis, you set the operation mode to quasi-transient, and then, just as in a transient analysis, you'll set the solver setup for a total time of simulation and either a time step or number of steps. That doesn't really affect the solution. It'll affect the way the time signals are displayed as you edit them, which I'll show you. You define the boundary conditions or the impressed E fields as time signals, and then you run the trajectory and field analysis as you normally would. Now I've prepared a very simple model of parallel disks which will illustrate how you would perform a quasi-transient analysis. So we'll begin with a simple static analysis. So what we have here are two disks, and I've made portions of them invisible. The top disk has a zero potential and the bottom disk has a positive potential, so that produces an E field in the Z direction. And I'm launching a positive particle with a certain velocity against the E field and also a certain velocity which is parallel or perpendicular to the field. So what happens is that you describe a nice parabolic arc. It takes about 10 microseconds, and at the halfway point, or 5 microseconds, then you find that all the velocity in the negative Z direction has been exhausted, and so the particle is essentially traveling in the positive Y direction. Then, as it proceeds further, the field in the Z direction begins to push it up again. So I'll show you now how we'll convert that into a quasi-transient analysis. First I'll show all the components and remove all transparency. And then we'll switch from a static analysis to quasi-transient. And then we'll switch our solver setup to a total time of 10 microseconds and a step time of, say, 0.05. And as I said, this really doesn't affect the solution. It just allows you to visualize the time signals. So now, if we look at our boundary conditions, what's happened is that the constant boundary conditions from the static analysis have become sources in the quasi-transient analysis. They're very simple sources, though. The top disk has a constant zero potential, and the bottom disk has a constant potential of about 50 volts. If we were to run a transient analysis now, or a trajectory analysis, we'd have exactly the same result as the static. So we'll change these signals to make a more interesting result. So first we'll open the source manager and we'll just change the names. So the top disk, instead of constant source 1, I'm going to call that neutral. And the bottom disks, I'm going to call that now variable. And now we're going to change those time signals. I'm just going to change the variable time signal. So far, it just has a constant value of 50 volts. And to make the trajectory more interesting, let's switch it off at the halfway point. So there are different ways of doing that. One way would be to add a step function which has the opposite polarity. So I'm just going to copy this value, and then I'm going to add a new time signal, which I will call minus step at 5 microseconds. Now, we can define this time signal using any of the library of standard signals we have. We could create a function, or you could even enter values from a table that you've prepared from a spreadsheet. In this case, we can use one of our standard time signals. And I'm going to use a step source that I'll start at time t equals 5 microseconds, and its value is going to be the opposite of the initial. And we're going to add those signals. You can either add or multiply signals together. So when we add this step at 5 microseconds to the constant signal, what we should have is initially 50 volts, and then when you add the minus 50, it should be 0. So let's plot the source. And that opens up an autograph. We'll make the fonts largest so you can see what happens. So basically, for the first 5 microseconds, it's exactly like the static analysis would be. And then at the 5 microsecond mark, we switch off the field. And now you notice the source table also contains a summary of that information. It shows that the neutral is still that constant 0 potential, but the variable starts off at 50 volts, and then at a time of 5 microseconds, we add minus 50 volts to it. Okay, so now I'm going to hide some of these volumes so we can see the trajectory better. And just to show you, the emitter I have is a point emitter. And it's been defined with direction numbers in the positive y direction and the negative z direction to give it that parabolic arc. So now we'll launch the trajectory again. Now first the program is solving for the new field conditions, and then it's solved for the new trajectory. And just as you would expect, if we turn the voltage off at exactly the right time when the z component of the velocity is 0, then the particle just continues on in the y direction because it has only a y velocity. Now we could make this a little more interesting if instead of just turning the field off at the halfway point, we reverse the polarity, then we'd have another parabolic arc describing in the opposite direction. So let's do that now. Let's go to Physics, Boundary Conditions, Voltage, and let's edit that variable source again. So now, instead of adding in the opposite time signal, I'm going to multiply by an alternating pulse. So we'll change this to multiply. We'll rename this time signal to alternating pulse. And instead of a step source now, we're going to have an alternate periodic pulse source. It'll start at time t equals 0 with amplitude 1. The pulse width will be 5, and it'll have a total period of 10. So what that's going to look like now So once again, for the first 5 microseconds, it's at 50 volts, but then at 5 microseconds, the polarity will reverse. And once again, we can run the solver. And as you would expect, now the trajectory during the first part is exactly like the static trajectory. And then when we reverse the field, it describes a parabolic arc in the opposite direction. Now I wanted to come up with a little more interesting example to show you the power of the quasi-transients. So I came up with an idea of having a more complex sinusoidal function. So here, if you look at the boundary conditions, I have what I call a multi-frequency source. which consists of 150 kilohertz, 210 kilohertz, and 300 kilohertz. But if you look closely, they don't all occur at the same time. One starts at 0 seconds and ends at 9.9. The other starts at 10 and ends at 19.9 microseconds. And the last source starts at 20 and ends at 30. So the way I did that, we can have a number of cosine sources. So in this case, we have 150 kilohertz that starts at time t equals 0 and ends at 9.9. We have a 210 kilohertz source, and that starts at 10 microseconds and finishes at 19.9. And a cosine source, which starts at 20 microseconds and ends at 30. And we also have an amplitude factor that I just multiply in. So now if we look at that source, initially you have the 150 kilohertz, and then you switch to 210 kilohertz, and finally you have 300 kilohertz. And what you're seeing here are three separate emissions. The blue emission starts at time t equals 0, and it experiences the 150 kilohertz sinusoidal variation. And then after 10 microseconds, it actually hits this rectangular surface, which is a collector, so it ends. The second emission begins at time t equals 10 microseconds, and it sees the 210 kilohertz signal. And the last emission begins at 20 microseconds, and it sees the 300 kilohertz time signal. And that's easy to do. If you look at the emitters, you can set emitters to begin at any particular time. So what I have here, I have 3-point emitters that begin at slightly different points and at slightly different times, and that way they correspond to the change in the time signal. So this is exactly what you'd expect from an analytic solution. It turns out the amplitude of oscillation is inversely proportional to the square of the frequency. So the 150 kilohertz amplitude is 4 times the 300 kilohertz amplitude. The 210 kilohertz is about the square root of 2 times in frequency, so you get about half the amplitude. Now the last example has an even more complex time function. And what I wanted to do there, instead of having the frequency change in discrete steps, I wanted to show you how you could use a function definition in order to make the frequency vary continuously and also the amplitude vary continuously. So here I have a new source called variable frequency and amplitude, and you have an amplitude function, which is a linear function which increases with time. You have a sinusoidal function in which the frequency is not constant but also varies linearly, and finally you have a constant amplitude. So to show you what that's going to look like, so here we have our linear amplitude function, our linear frequency function, and finally I have a constant amplitude function which I needed to produce the correct voltage. So I'm going to just change that temporarily to 1 volt, and then I'm going to plot all the components. So here we're seeing the results just to show you how you can create a very complex waveform. The green linear function is the amplitude function that varies linearly. We have a cosinusoidal wave that varies linearly in frequency with time, and we have our constant amplitude. And when you multiply those all together, you get this red complex waveform which is increasing not only in amplitude but in frequency. And the result of this complex waveform is this sort of a trajectory. So basically you can define almost any time signal that you can think of using either the functions or our standard time signals. So now I'm just going to quickly show in the last section of our presentation some of the features we've added for importing and healing CAD files. We can now directly import SAT and STEP files. We have healing commands. Normally when you import a CAD file, almost always there'll be some errors that you have to fix up. And I'll show you ways we've developed for cleaning up unconnected geometry and NURBS data. So we always had links to the major CAD packages. In some cases you may be using a CAD package that we don't have a direct memory link to. Almost all of them can save as either a SAT or a STEP file. So we can import those directly, and we can also save them directly if you want to reopen our files in your CAD package. When you import a CAD file as a STEP or a SAT file, whatever name was initially signed, that will become a named object in our software. Now I'm going to show you one of the more common problems that occur when you import a CAD file, and that's a mismatch between a surface and the boundary curve defining its edge. So here is a typical example of a group of surfaces that you might have imported from another CAD package. And the most glaring error, you can see we have an edge curve and the surface of the edge does not coincide with the edge. So we have a command for fixing that. Now, all of the surfaces, in fact, in this model have some sort of a problem. So it's detecting them one by one. I'm just going to fix them. And the last surface with that problem has been detected. That's the one that I pointed out. That was the most obvious one. So now, once we fix those problems, the surfaces coincide with their edges. Now, also when you import a CAD file, or even when you're just working with our software, you may create extraneous segments and surfaces and points, and you'd like to clean those up without having to go through your model and find them and select them individually. So we have a tool, or a series of tools for fixing that. So here I have a model with disconnected segments and surfaces and a disconnected point. We'll go to Clean Up, and first we'll clean up the unconnected point. So the program has found that automatically. I'll enter yes, so it'll be fixed. Then I'll run the command for cleaning up unconnected segments. Now you notice it found this segment first, and even though both endpoints of the segment are in fact connected to surfaces, for our purposes we consider that to be an unconnected segment. Unless a segment is part of a boundary of a surface, we consider that unconnected. So I'll delete that. And finally, I'm going to clean up the unconnected surfaces. Once again, even though this surface has one edge which coincides with the volume, we consider that to be an unconnected surface. So I'll remove that and the other two. Now the last example I'll show you is how you would clean up NURBS data. In CAD packages, the curves are almost always defined as some kind of a NURBS. And that's not bad in itself, but once you import those into our software, if you could take a series of points which are on a line or on an arc, instead of having those defined as a NURBS curve, if we can define those as line segments or arcs, we can use analytic methods to deal with them, and they'll also take less memory. So it'll be a faster solution, a more accurate solution, and it'll take less computer memory. So I've created a model where I deliberately broke up some line segments and some arcs and then connected them as NURBS curves. So I'll show you how that works. So here's my model. We'll run the geometry cleanup NURBS data. Now, the program requires some input from you. It has to have a length tolerance. Basically, that's a tolerance which says if you find 2 points which are within this tolerance, they're to be considered the same point. So we'll accept the recommended default of 1e minus 8. Now the program is asking for a percentage tolerance for data reduction. What that means is that if you see a number of points which appear to be on a line, they may deviate slightly, so the program has to know what is the tolerance you'll accept. How far can they deviate before you want them to be made up into several lines instead of one line segment. In our case, we'll accept the 0.1%. What that means is that if the points are within 0.1% of the total length of the new line, we'll consider them to be on the line. So we'll accept the 0.1%. Okay, so it has found the first line, or the first NURBS curve which could be converted into a line. Now, it asks, do you want to convert that? And it says Y for yes, N for no, A for all, or S for skip. I'll go Y for yes. And now it's found the second one. I'll fix that one. And now I'll just go A for all, and I'll let the program automatically fix the rest of them. Now, you notice all the line segments, or the NURBS that were consisting of straight line points, have been converted to line segments, but none of the arcs were. And that's because, as I said, I created this model by artificially breaking up the arcs into a series of points, and the resulting points don't quite fall within that 0.1% tolerance. So I'll run the command again using a tighter or a looser tolerance. We'll go geometry, clean up NURBS data, and we'll use the same length tolerance. But this time, instead of 0.1%, I'll use 1% so that it'll be very easy for the program to detect and convert them. So it's found the first arc, or first NURBS that could be converted into an arc, and I'll fix up the rest as well. Okay, so that concludes the formal portion of our presentation, and now I can deal with any questions that you might have. I have a question about what would be the difference in the results of a transient in quasi-transient. Okay, again, the main difference in between a quasi-transient and a transient is that in a quasi-transient you assign potential conditions, which are our time functions, and then we perform an actual field solution which utilizes the permittivity and conductivity values. Okay, where in a quasi-transient, we're assuming that the fields can be switched instantly, and so the time function of that the field will, or the trajectory will see, we assume we have some kind of a infinitely powerful source which can switch voltages, and so you don't actually need to perform the full transient. So in terms of difference in accuracy, it all depends on what your actual time functions would be. Let's say that you did run a transient function and you found that instead of the voltages switching according to a step, they switched according to some sort of an exponential approach. You could actually define that as a quasi-transient, and then the results would be exact. Okay, well, it seems that that was the main question we had today. So now I guess we'll bring our presentation to a close. We'd like to thank you all for attending, and we hope that you will attend our next webinar.